Okay, so in this one, we talk about components. And a little later on, next week, we'll get into the circuits. So we'll talk about actual resistors, capacitors, inductors, batteries, diodes, transistors, schematic diagrams, and resonant or tuned circuits, and some other components. Probably only do resistors, capacitors, maybe inductors today. I forgot how many's in this one. So remember, the function of a resistor is it opposes the flow of current regardless of frequency. So it doesn't matter if it's AC or DC. We represent it with R and specified in ohms. The higher the resistance, the lower the current's going to be. In the physical world, these come in kind of fixed values that you can buy. You know, like 220 ohms, 330 ohms, 470 ohms. There's kind of a standard there. And they get kind of in between values when you get up to the higher percentage ones, which means the accuracy of them. When you get up to the 1% or less than that, 0.5%, 0.1%, you can get them down to, you know, fractions of an ohm, basically. They also come in a variable form, which we call a variable resistor. Normally, you're going to see that as a potentiometer, and it'll be a 3-terminal device, which is basically a resistor with a sliding contact, okay, that can make contact with the resistance portion anywhere between N1 and N2.
Like a light switch.
Hmm?
Like a light switch. One of those dimmer switches.
Well, yes, okay. When we use those in the audio world, we usually use it as a volume control. And that knob on your radio that controls the volume, at least for older radios, would be a potentiometer. In modern radios, like amateur radio stuff, the knobs are all encoders, digital, and acts like a potentiometer. And you also see it as a voltage adjustment, like on power supplies and things. That's where they're normally used. The symbol that you see on a schematic for a resistor is this jagged line. There's usually 3 of them. And this over here is a picture of normal from power resistors on down to some of the very small, like 1/4 watt and stuff. I didn't show any of the surface mount because they'd almost be too hard to see compared to these others. Even the largest size, the 1206s, are 1/8 of an inch long. And then they go down from there. You need magnifying glasses and stuff to deal with them. The potentiometer, okay, is a similar symbol with this slider. Now, if it's shown with this center terminal connected to one of the ends, then it can behave as a variable resistor. So the resistance between this end and this end is going to vary depending on where it is, because it's essentially shorting out this part of the resistor. When it's used as 3 separate terminals and we have a voltage across it, depending on where it is, the voltage is going to vary. So if I had 10 volts at this end, if I move the slider up here, I'm going to have 10 volts. I'm going to go all the way down to, say, 0 volts at this end. And that's where the potentiometer name came from, because it's a measure of the potential. So what electrical component opposes the flow of current in a DC circuit?
The
Bravo.
If you met Bravo. is it right? Oh, let me go back, let's see. Was there any of these? Oh. We haven't talked about inductors yet, but one of the differences to remember is an inductor opposes the flow of current in an AC circuit. Okay. It does not oppose the flow of current in a DC circuit. This looks like a conductor. Inverters are used to convert DC to AC, like you know, for mobile, like in your car, if you wanted to have a plug in an AC thing, you'd use an inverter. And transformers just transform current. There's no gain. They, you know, depending on the turns ratio, they can transform 120 volts into 12 volts. At a higher current, the power in is going to be equal to the power out. So there's no gain in a transformer. So what type of component is often used as an adjustable volume control?
See,
Charlie.
Charlie sounds good. What electrical parameter is controlled by a potentiometer?
Resistance.
Yeah, bravo.
It can't control inductance, it can't control capacitance, and can't really directly control field strength. Okay, so capacitors is our first frequency sensitive component. They're made of conductive surfaces. They start off being metal plates separated by some form of insulator, which we call a dielectric. One of the first ones was a Benjamin Franklin square, which was a glass plate between two metal plates. And actually it was a capacitor. The glass was the dielectric. And it will store charge because it creates an electrostatic field between the two plates. So when you apply a voltage to it, it will charge up. You'll get current flow or charges flowing into one plate, like the negative charges will go to one side, and you'll have the positive charges, or which the atoms that have lost an electron, because they'll appear to be positive on the other plate. That creates a field and actually a force between them. So if they're opposite polarity, they're actually squeezing, those plates would be squeezing on the glass. And I don't know if we get to that in this course. That's kind of the way piezoelectric crystals work, because we take that crystal material, which is sensitive to pressure. If you squeeze it, it will produce an electrical current. So if we put plates on there and apply a voltage, okay, that causes a force between the plates that squeezes on that crystal, which will cause it to generate a voltage. And if we put it in a circuit where it gets some feedback, that's how we make an oscillator. And it'll sit there and we squeeze it and unsqueeze it based on the current coming back. So basically, a capacitor is a storage device that stores energy in an electrostatic or an electric field, as opposed to a magnetic field, which we'll talk about next for inductors. And the ability to store energy in that electric field we call capacitance. So the amount of energy that it can store is measured in capacitance in farads, named after Michael Faraday, because he did a lot of research with that kind of stuff. And we use the F in Faraday to represent farads. And a farad turns out to be 1 coulomb of charge per volt. So if we charge that capacitor up to 1 volt, it's going to have, and if it was a 1 farad capacitor, it would hold 1 coulomb of charge. Now, that's a lot of charge. And a 1 farad capacitor used to be very, very large. Now there's supercapacitors where you can, I think you can get farads in an extremely small package at very low voltages. And one of the uses for them, turns out, is in pico balloons, where people launch about a 3-foot diameter balloon with hydrogen in it, with a little tracking device, and track it as it goes around, if they're lucky, as it goes around the world. And because it's up about 35,000 feet, the temperature is -65. Batteries don't work like the people are discovering with their electric cars up north. So they use supercapacitors from the solar cell to store the energy because they still work at those temperatures. This is a picture of all kinds of capacitors, the kind you typically would see. These are ceramics. Can't say I've ever seen too many of these 3-terminal ones. Sometimes you'll see axial leads, usually on an electrolytic, which is slightly different in that instead of just a straight dielectric insulator, it has a electrolyte compound like you find in some of your batteries. And it will allow it to store a lot more charge than you would with a straight dielectric. You can get these in very small surface mount packages. You see them for motor run and start capacitors on big motors. You've got some in your appliances at home. If you've ever taken the cover off of your washer or one of those things where there's a motor in it. PC mount. This is a little trimmer that actually has plates, 2 sets of plates, where one set can rotate so they mesh or interact with the other to vary the amount of capacitance depending on the area of overlap. And that's how we used to tune radios with bigger versions of those and many, many plates. And you would vary the capacitance. And still in antenna tuners, which isn't really a tuner, they still have variable capacitors like that with multiple plates.
Am I reading this right? There's 3 versions of capacitors that are made from oil products: polyester, polypropylene, and polystyrene.
Oh, at least.
So all the nutbag environmentalists, they can take all those plastic bottles that they bitch about and turn them into capacitors?
Yeah.
Okay.
Well, I don't know if they actually recycle that way,
That's a
but-
business idea right there.
but
Yeah.
that's one of the uses for oil.
Okay.
And electrolytic capacitors.
We use oil. I mean, forget about cars. We use oil in so much stuff.
I know, for everything, but it's just another part of the argument.
Yeah.
Looking at big electrolytic capacitors, a good reminder, I'll put my safety hat on. They are something that you can have things unplugged for some time and still get knocked on your butt with the amount of current in them.
Oh, yeah.
Old TVs were really a biggie for that.
We talk about that in the safety portion to make sure that they're discharged before you go mucking around. Particularly in some things like with tubes where you've got 300-400 volts or more. Well,
Yeah.
In fact, in my linear amplifier, it's 1900 volts. That will really knock you on your ass.
There you go.
Okay, so a capacitor is essentially two plates separated by some form of insulator. And it stores charge by creating a field between those two plates. So we'll have a positive charge on one side and a negative charge on the other. The distance between the plates is part of the formula for the amount of storage or capacitance. The closer they are, the higher the capacitance, the larger the area of the plates, the more capacitance. And when they started building these, you notice none of those pictures I showed you look like big flat plates. Well, they got the idea, well, I can like take two pieces of aluminum foil, put a piece of wax paper between it and roll it up. So most of those round ones are actually built that way, unless they're electrolytics. So it's a very large plate rolled up. Now, in the case of the ceramics, they are a piece of usually round ceramic with plating on each side to make the plates. And sometimes those are multi-layer to get more capacitance. So when we have a capacitor and we apply a voltage to it, and in this circuit, I put a resistor in here to control the amount of current. Because if there wasn't one there, you wouldn't see anything on this plot because you'd have almost an infinite current for a very short period of time and charge it up. Since the current's being limited by this resistor, okay, you see the voltage go up, okay, as we charge that capacitor. Now, it turns out that the product of the capacitance and the resistance is what we call a time constant. So if you multiply those two together, you get the time constant in seconds. And in one time constant, this will charge to 63 point something % of its final value. In 5 time constants, it will be over 95%. So it exponentially, I guess in theory, it would never get there, but it does. So that kind of comes up later when we talk about time constants and some things. The same thing for discharge. It works the same way. It will discharge at 63 point something %. Just think of it as 5/8. It's close enough in one time constant. So what type of electrical component consists of conductive surfaces separated by an insulator? What electrical component stores energy in an electric field?
Bravo.
Bravo. We hadn't talked about varistors. That's a voltage controlled resistor. And we hadn't got to inductors. That's next. And they store their energy in a magnetic field as opposed to a electric field. And diodes don't store, well, not technically correct because they do have some capacitance. But for all practical purposes, they just pass current in one direction. What describes the ability to store energy in an electric field? The ability to store it.
Capacitance.
Yeah.
Good old delta. What is the unit of capacitance?
Alpha.
What is the unit of capacitance?
Alpha.
Now, I think that should be capitalized, but it's not on the question pool. But I did it here. And like I said, 1 farad is equal to a coulomb of charge at 1 volt. It's a big capacitor. And when we talk about inductors, then we'll talk about henries, which is the unit of inductance, which is now. So inductors are just essentially a coil of wire or a conductor coiled up. Even a straight wire actually has some inductance because it creates a magnet as current flows through it, it creates a magnetic field around it. So when you put them together in a coil, it allows the magnetic fields to combine together and basically concentrate. So it increases the inductance when you wind it as a coil as opposed to a straight line. So if you had a meter of copper wire with an amp through it, it's going to have a small amount of inductance. If I take that same wire and I coil it up close together, I'm going to get a lot more inductance just because I have the magnetic fields interacting with one another around the wire. So the basic thing is to remember that it stores its energy in a magnetic field. When we talk about emissions, radio waves, electromagnetic waves, light, for instance, it's the same thing, it's just a higher frequency, are composed of an electric field and a magnetic field that are 90 degrees opposed to one another. So that's where a lot of this comes about, and we'll talk about it when we get to the emission part. The ability to store that energy in the magnetic field is called inductance, where we call it capacitance in a capacitor. We call it inductance in an inductor. And we measure it in henries, named after some guy, Henry. I can't remember his first name either. And here you can see the magnetic lines of force all concentrating in the center. So you get a much higher magnetic force there. And that's what increases the inductance when you wind it into a coil. Now, the number of turns increase, well, more turns is more inductance. The larger the area, in other words, the bigger the circumference, the more inductance. And I don't have the formula on here. You don't need to know it. Well, actually, there it is there. And it's another one of those things with pi in it. In this case, we're showing, and most of the inductors you'll see nowadays are made with toroids. It's usually a ferrite, which is a mixture of different kinds of iron oxides and some other oxides pressed together in the form of this little toroid or donut, which has much higher permittivity than air does. So it increases the inductance. And the one thing you notice, all those magnetic lines of force are inside that core. So there's no magnetic, or essentially no magnetic lines of force outside of that. So it won't interact with another coil next to it. Whereas in your other coil, you have to be careful what it's next to, because it can have an effect from another coil or another component, it's why that's about all you see nowadays is toroid inductors. So I did the same kind of circuit with the limiting resistor, applied a voltage to it. And you can see that initially it appeared to be, because it is initially resisting current flow to that step function. So it appeared to be 10 volts. As the current flows and it charges up the magnetic field, the voltage that we see across that's opposing the current flow decreases. And again, you got a time constant thing. And out here, it's essentially a short circuit or just the resistance of the wire itself. But you do have energy stored in that magnetic field as long as that current is flowing. When we stop the current, take the voltage away, okay, the field tries to collapse, then it actually tries to create an opposing magnetic field, and that's why you see this voltage spike in the negative direction and see it decrease as the energy dissipates.
Question. Car reference. Alternator in the car,
Okay,
has that winding,
all right. There's several of them actually.
so what plates in them? Well, I think there's a contact point in the line, right? What
Well,
goes-
not on an alternator, but
Yeah, what goes bad on the alternator? That they-
the diodes.
The diodes are what go bad, so when they
Right.
build them, they're just pretty much replacing the diodes.
Usually, and it's all on a little heat sink board, and they just replace the whole thing
Okay.
and charge you half as
That's
much
pretty
as the
about-
alternator.
Stupid money that doesn't need to be spent, but that's okay.
There's the difference between a generator, a DC generator that's used to have in cars, and it used a commutator or in order to make the contact, because they had to change the field as it rotated.
Okay.
In an alternator, it's a polyphase generator. I don't know if they're using 6 or 12, whatever, but they go through diodes to rectify it back to DC. So you're actually getting pulsing DC out of that alternator.
Okay.
But a lot of pulses because
So
of,
Oil that actually never goes bad, it's just.
well, it shouldn't.
Right.
I mean, from normal wear and tear.
Right.
Bearing might go bad.
Right.
But normally it's the diodes for some reason. You were
Oh,
drawing
heat.
too much current for too long and overheated them.
And that toroid coil. The first machine to manufacture those was invented in 1959 by Ed King for Collins Radio. They tried to mess him over. He wound up in a lawsuit with him and used the money to create King Radio, which is now Honeywell and Bendix Kings.
Okay.
He was my neighbor also at the time.
So what electrical component is typically constructed as a coil of wire? Delta. What type of electrical component stores energy in a magnetic field? Charlie, right? That's the difference. Magnetic field for inductor, electric field for capacitor. What describes the ability to store energy in a magnetic field? Inductor is inductance. Measured in what?
Paris, Henning,
Henrys. What is the unit of inductance?
the Henry.
Shouldn't it be capital?
Yeah, I think so. Because it is a proper name. I don't know. They're not consistent. Except on abbreviations. And there's a trick question there. You gotta remember the small k, capital H. Okay, batteries. Well, we kind of have two kinds. We have non-rechargeable batteries, which are your typical carbon zinc type that you have in mice, flashlights, whatever. It's a chemical reaction, and once it's finished its chemical reaction, it doesn't produce voltage anymore and it doesn't work. And there's no way to recharge it.
And then it corrodes and ruins your equipment.
Right, because that electrical process in those cases is not reversible. In the case of rechargeable batteries, it's still an electrolyte, but it's a reversible process. So when you apply a voltage and current to it, you can recharge them. This is showing a kind of a typical lithium ion battery. Which most of the batteries rechargeables today are lithium based, whether it's lithium ion, lithium iron phosphates are becoming more common for replacements for the gel cells, like the 12-volt batteries. Lithium poly batteries, which are mostly used in radio control airplanes and stuff because it's a very high storage to weight ratio. They also have the bad habit of catching on fire. And a lithium fire is extremely hard to put out. It requires a type K fire extinguisher, or D, I forgot. But I've got one. You got to buy a special fire extinguisher. And they've been known to melt their way through the truck bed of a Jeep. Somebody left his airplane in the back and the battery was damaged because he got upset when it crashed and he tossed it in the back and the battery caught on fire and it's hot enough to melt steel.
I'll give you a little side story. If you own an EV in parts tow companies will not tow you if you own an EV,
Really?
because the insurance companies who insure the tow companies know the risk of the fire. And what they're concerned about is it being on the tow truck, not being able to get the burning vehicle off the tow truck, plus the damage of the road,
Yeah.
burning through the road. So they're telling them, if you were to tow EVs, your premiums are going
Yeah.
stupid high, to the point where the tow companies are going, not worth towing you.
Go back to the type where you pull it instead of.
No, they just won't.
Because the road.
No, because
Yeah.
even if it's on the hook where they're dragging it on the wheels, if it catches on fire, a lot of times they can't get it off the tow truck.
The road.
Or the road, it burns through the road, and the cost of repairing the road that has that much damage, it burns through the tar.
Oh, I guess when you're the tow truck, you're in charge of the road as well, right?
Yeah.
You're in charge of
Yeah, yeah.
Yeah, they got to pay fees.
Right.
Yeah, I didn't think about the road, but I remember years ago at one of the NASCAR races, there was a giant wreck and stuff. There was fire everywhere and it burned up a lot of the asphalt on the track. It took a lot to repair it.
Mhm.
It wasn't just hauling the cars away. They couldn't race.
Right, exactly. That's just something that's come out of this, the EV stuff where people are, I don't have a gas bill, but the
Yeah.
insurance on your EV because of the undercarriage damage destroying the batteries.
Yeah.
The insurers don't want to insure it because they haven't come up with a protective enough undercarriage to keep the batteries from getting damaged.
And
Yeah.
Halon is one of the fire extinguishing units that'll do a good job.
That's gotta be dangerous.
Yeah,
It sucks the oxygen out of the air.
right. It's not good for humans.
Right.
And
Yeah, it'll kill the people.
And they're worried about the hole in the ozone layer. And so they have banned most of the halons,
So it's difficult in getting, even if you want to deal with it. Yeah.
but it's still better than the old NiCads.
Yeah, but they didn't create as many fires. So basically, in the rechargeable, we've got the old lead acid batteries, which still are around. They're still probably the best thing going for
the charge.
long-term storage, deep cycle, things like that.
I used to work at a trucking company that ran their forklifts on that, believe it or not. The batteries were enormous.
Yeah,
We needed to use a hoist. The whole back of the forklift was the battery, and we used to need a hoist to pull it out and put the new one in. But the actual motors or the actual forklifts, when I got there, were pushing 25, 30 years old. The company had been in business for 35 years, and it was the original fleet of tow motors that they had, which from a business standpoint, owning a piece of equipment for 30+ years. Took the thumbs up.
well, that was, I guess, the big reason why we didn't have electric cars in the past, because the battery technology, you know, lead acid batteries are just too big and heavy to be practical. So they really had to develop newer batteries to make it even possible to do 300 miles.
Yeah, but for a forklift operation and for.
Right, that's,
What it works.
and you can charge them
Right
as
there.
fast as you need. The nickel cadmiums are still around. They were more popular for portable stuff. Most of the newer, like handheld radios and things, are using one of the probably lithium ion batteries, possibly nickel metal hydride, which is kind of another variation like the nickel cadmiums. But all of those are rechargeable, whereas your carbon zinc, like flashlight batteries, or the alkaline version, or the mercury that you see in like hearing aids and, you know, the button cells, a lot of those are mercury or alkaline. None of those are rechargeable. So that's the main difference. And the question is, which of the following battery chemistries is not rechargeable?
Carbon, zinc.
Which of the following battery chemistries is rechargeable? Well,
All of the above.
it's one of those. Yeah. They're all rechargeable batteries. Okay, so we learned again, resistors oppose current flow to AC or DC. Potentiometers is an adjustable resistor typically used as a volume control or a voltage control. Capacitors store energy in an electric field. It's made from conductive surfaces separated by an insulator or dielectric. Inductors store energy in a magnetic field, usually consists of coils of wire. And batteries store energy in some form of electrolyte. And we have rechargeable and non-rechargeable.